Great. Welcome to the last and 19th and final lecture for convex optimization this quarter. It's been a pleasure to be with you, even though we can't really meet each other. And it's been a great time teaching you guys about some of these topics that I'm excited about. Today's the last lecture. So what I'm gonna do is that I'm gonna finish what I left off with in the last lecture on ADMM and finishing the last example on some clever trick to do ADMM decomposition, which gives you the computational benefits sometimes. And then I will move on and move to our final advanced topic lecture on adaptive online learning. Okay, where I'm going to address some of the questions that were posted on Piazza about the weakness of online learning and maybe how we can design algorithms that can do better in the dynamic and non-stationary situations. Okay, so we'll first move to the end of the last lecture. So last lecture we talked about ADMM, and we actually talked about two other algorithms as well. We talked about the dual descent, which is essentially a gradient descent on the dual, and then we talked about one way to make it to make it more and more useful and more stable in practice and converging faster using the augmented Lagrange multipliers, which is in some sense dual to the proximal point algorithm. So but the key motivation of the dual descent, which is that the objective function decomposes by coordinates, and in the dual it becomes dual separable, and you can in some sense optimize these objective functions in parallel. That property is no longer retained by ALM. That's why we introduced a new set of algorithm called the alternating direction method of multipliers, which aims at resolving this issue. So turns out ADMM is quite general. So specifically, ADMM solves this kind of problem when you have two objective functions, fx and the gx, and that you can split it by introducing this dummy variable z, so that you have two functions with different coordinates that you minimize over, subject to an additional constraints. Okay, so this is a form that ADMM optimizes, and the way that it optimizes, it's very simple. You basically construct the augmented Lagrangian, and then you solve argmin for x, you solve argmin for z, and then you do dual gradient ascent on the dual variable u. Okay, so by iterating this, it has been shown that ADMM algorithm converge in both the objective function, in the residual, and in terms of the dual variables. So ultimately you end up getting the optimal solution, and the convergence rate is more complicated than the standard first order methods, but in practice it behaves more or less like first order methods. And sometimes it's significantly faster, and then it behaves more or less like the second order methods. So you can think about ADMM to be an algorithm that sits in between the first order methods and second order methods. Yeah. On the one hand, it is just gradient descent on the dual. On the other hand, it does quite a bit more extra work in the primal when you keep finding the exact minimum on x and z. And it is alternating direction because it is alternating the direction between optimizing towards the x direction and optimizing towards the z direction. And it's quite remarkable that this actually works in a very general sense. Okay, so the second part of the last lecture was about looking at examples of ADMM, and then so we talk about example on lasso, we talk about examples on group lasso, and well the sparse PCA problem, which are examples that we have been looking at for a while, and some of these examples appear as early as I think lecture 2 or like even lecture 1. Okay, And there's this robust PCA problem, which falls directly into the ADMM form, where you want to decompose an observed matrix M into a low rank component and a sparse component. Okay, so this turns out that like directly minimizing this is somewhat difficult, but ADMM, with ADMM, this becomes very straightforward. Basically, you are dealing with this trace norm or nuclear norm objective, and then deal with the one norm objective, like one at a time, and then you try to combine them and then make sure that the solution satisfy does not move too far away from your observation using the third line. Okay. So there are some practical examples as well, and then we got to this consensus ADMM where we introduce one more dummy variable x, so that we can split these things into two blocks rather than B blocks. So that allows us to run ADMM without worrying about not falling into the standard format, because we can concatenate this x1 to xb together as one update. So call that z, right? Call x1 to xb. Call this z variable, and then it becomes a standard ADMM. And because of that, we can do because of this formulation, then everything becomes decomposable, and we can solve the first objective in a distributed system or in parallel. Okay, so that in some sense addresses the problem that we started off with, and addresses the limitation of the augmented Lagrangian method. Okay. It can be generalized, and I think what we are left with is this slide on the spatial decomposition. Okay, so like many other algorithms, when an algorithm works, and there's no single optimization algorithm that dominates all the other algorithms. Like in all problems, for each problem, if you consider the special structures of the problem, you might be able to solve the problem a lot faster. So we've seen several examples in this vein. And sometimes the first order method is the most appropriate method. And in other cases, when you want high numerical precisions, and Newton's method or interior points methods are the desired choices. And then sometimes you can even implement the Newton's method and interior point methods with every iteration cost proportional to the size of the problem rather than polynomial in the size of the problem. So those are the cases when using the more complex solvers are really beneficial for your specific problem of interest. Okay, so the same story goes for ADMM. So sometimes we can decompose things differently in ADMM and then leverage more specialized solvers so that at the end of the day, we get a linear time updates for all the 3 update rules in ADMM, and then suddenly ADMM becomes a more appealing algorithm in practice. Okay, so I'll give I guess 2 examples on such a spatial decomposition, just to illustrate how useful ADMM is and how flexible it is in terms of algorithm design. Okay, so the first example that I'm gonna give is train filtering. So we've seen this kind of objective function. So we have a quadratic function that we want to minimize, and we have a penalty in the form of the k plus first order discrete difference operator. Okay, so I'll make it a more concrete example. So D1 is the kind of matrix that looks like -1, 1, -1, 1, -1, 1, -1, 1, right? So it's almost a diagonal matrix. It takes adjacent differences of the points. And you can recursively apply this first order difference operator and then construct the second order and third order difference operator. For instance, the second order would be 1 minus 2, 1, 1 minus 2, 1. You have this convolving kernel in the middle that resembles the discrete derivative of the case order, of the k plus first order. Okay, in the third order derivative, so D3 will be like minus 1, 3, minus 3, 1, minus 1, 3, minus 3, 1, minus 1, 3, minus 3, 1. Okay, so this kind of operators are extremely specialized, right? So it's special in the sense that everything else is 0, it's sparse, and it is somewhat diagonal. So maybe let's try deriving the ADMM algorithm for this problem, like with a special kind of decomposition. Okay, so let's see. Suppose we instead of decomposing this dk plus 1 using this way, or simply take z to be dk plus 1 theta. So if you do this, right, so one of the prox operators that you end up needing to solve in ADMM becomes a self-thresholding operator, which is not bad because you can solve it in linear time. On the other hand, like maybe we can leave one of this. So notice that dk plus 1 is equal to d1, d1, d1. Each one of them with a shrinking dimension. So the first one is dimension n minus 1 times n. The second one is n minus 2 times n minus 1, and the last one is like n minus k minus 1 times n minus k. Right? So you have you can construct this differently, but suppose we group all these together and leave just one of these as follows. Then we can come up with an ADMM algorithm that a reformulation subject to a more non-trivial linear constraint, and a more non-trivial like penalty regularization term right here. Okay, and suppose we write out the okay, suppose we write out the ADMM updates. So let's do that as a quick review. So theta minus y plus lambda. Let's not worry about this d theta 1. Okay, we are reformulating it as minimize theta minus y plus d z 1 subject to the k the is equal to the k theta is equal to z. Okay, and then we can write down the Lagrangian, which is simply okay, and plus this dual variable u transpose the k theta minus z, and plus augmented Lagrangian term with a parameter rho. Okay, so you got an augmented Lagrangian term as a function of theta, z, and u. Okay, so now the update rule would be to simply find R mean of L as a function of theta, fix z and then fix u. Okay, and this is step 1. And step 2, arg mean theta L arg mean z, and then theta the u. And third step would be the straightforward gradient ascent by simply adding the gradient to u, right? In a scaled form, this is what it is. In a more general form, you have the learning rate of rho right here. Okay, so let's take a look at what these problems would look like. Okay, so let's take a look at the first one. So check that in terms of theta, everything is quadratic, right? So you have a linear term, and the two other terms are quadratic, and this is in a form of solving a quadratic minimization problem with a covariance matrix with a Hessian matrix that looks like this, plus I theta transpose theta plus some b. So depends on which iteration you're talking about. But this is the key part, right? So notice that you have identity here. For the other term, like what do you get? This is actually like a banded diagonal matrix, which looks like this, and everything else is zero. So the bandedness depends only on k. So this is order k. Therefore, you can solve this linear system. You can solve this linear system of the form a theta equals to b in linear time n. Why is that? Since this is a banded diagonal, you can use Gaussian elimination, and that allows you to just get away with solving a linear system extremely fast. So in comparison to the general case where you have n cubed, this is not the interesting case because the same benefits you can get that from the soft thresholding based decomposition. Now for the second step, if we just look at what is the corresponding problem that we need to solve in terms of z. So notice that you have this term that depends on z, you have this linear term that depends on z, you have this quadratic term that depends on z, but with an identity matrix in front of z, right? So if you combine the second and third term and just do some manipulation, and you can see that this becomes a prox operator with respect to this function. This difference function, this sum of the absolute difference function, okay, with some, okay, and it turns out that this is this problem is called Fuse lasso, or total variation denoising. This kind of problem have a lot of specialized solutions. So in particular, if there's a dynamic programming algorithm to solve this problem exactly in order n time, or in the worst case. Okay, so in this case, we can like with this special decomposition, we get to make use of specialized solvers that has been developed for specialized applications to solve this problem a lot faster. All right, let's go back to this lecture. So the idea can be generalized to other cases when this D1, instead of being this simple difference operator of a sequence, we can talk about this D1 being -1, 1, and everything else for each edge in a graph. In a graph, a set of vertices and set of edges. So you can come up with this graph difference operator, and then the similar trick can be used to design ADML algorithm to solve this generalization of the problem, right? And in those cases, the linear system, instead of being a simple banded diagonal matrix where you can solve it with the Gaussian elimination, it becomes like a Laplacian type system. So when you have a Laplacian type system, there are multi-grid solvers, there are graph specifier based preconditioners that allows you to solve it in almost linear time, proportional to the number of non-zero elements. And for the corresponding prox operator, you can use the algorithm such as graph cut by Volkov and Kolmogorov, and also parametric max flow to solve those algorithms exactly in practically very fast like computation. Like sometimes all these methods, since they need to use it for computer vision applications, so a lot of them have extremely efficient C implementation that's out there. Okay, so I'll be very brief on the next example that I'm given. So you can also generalize this by choosing k to be 0, so that it becomes fused lasso, by generalizing this into multiple dimensions. In this case, you can so this is like 2D fused lasso, also called 2D total variation denoising. Okay, from Yu-Xiang, 1992. Okay, it's been extremely popular. So nowadays, total variation denoising based algorithm has been integrated in every smartphone, every like in Photoshop and in all the other cameras that automatically processes the digital images before presenting to you, even on the camera itself. So this type of algorithm penalizes difference operator by taking the adjacent pixels, takes the absolute value of their differences and sum everything up. So all of you have had the experience of developing an algorithm for this and trying out the standard solver for this in the first homework. So how do we apply ADMM algorithm to this? So it's like we can do the similar decomposition like before by taking z to be d theta, but well, like solving the prox operator becomes slightly more difficult. So you have to use this Boykov-Kolmogorov or parametric max flow for a particular graph that is a 2D grid. So even though they are fast in some cases, but they are not really a worst case linear time algorithm. So can we do better than doing this type of decomposition? So it turns out that we can alternatively like decompose things by let's see, let me skip to, yeah, we can decompose things by dimension. So basically we can have a theta 1 towards the x direction. We can have theta 2 towards the y direction, and then we can either do consensus consensus ADMM, or we can do just pick one of these things as a center. So notice that now everything decomposes because this clearly decomposes, and this decomposes into the first term and second term. And what are these first and second term? Each one of them are simply solving the univariate total variation denoising problem like in parallel for every row and every column of that image independently. Okay, so the more formal calculations of how these ADMM update rules are given here. You can see that every iteration is roughly linear in the size of this image, and it only takes a couple of iterations before you get a very reasonable denoised image. Okay, I'm gonna yeah. So here are some examples of how using this specialized ADMM can give you, and comparing to say the standard ADMM that uses a more simple decomposition with d theta equals to z, then you can see that the specialized ADMM converges significantly faster in practice. All right, so I guess that's the last thing that I wanted to say, and I've listed all the references about ADMM algorithms, about these examples that I give in the references. So so this is the paper for sparse PCA. So this is for the group fused lasso, and how do you design fast algorithm for that. For I think they have some energy-based applications there on smart grid. And robust PCA by Candice and Xiaodong Li, Yi Ma, and John Wright. It's right here. And this is the paper that deals with the the multidimensional Fuse-Lasso and total variation denoising and designing that specialized ADMM. Okay, there's some more work. So this is the order n time Fuse-Lasso solver, which has a very nice dynamic programming type of interpretation. The first ADMM algorithm for solving train filtering with a specialized decomposition appeared in Ramdas and Tijirani, and some of my work further generalized it to the graph and also coming up with a statistical analysis. Like all the other specialized solvers for parametrics max flow and graph cut, they have been extremely useful in computer vision applications that predates deep neural networks. Nowadays, deep neural networks are everywhere, but you can still think about how to make use of these specialized algorithms as building blocks in some of your architecture design. And that will hopefully lead to a significantly more powerful algorithm and inducing special structures in the type of deep neural networks that you wanna train without suffering almost any additional overhead in terms of computation. All right, so so I'll take I'll pause here, and in case you have any questions. All right, if not, let's move on to the last topic of the class. So on adaptive online learning. Let's flip to a new page. So so this is an advanced topic that's related to the second half of the lecture on online convex optimization. So let's give a quick recap of the setting of online convex optimization and how we are measuring the success. Okay, so OCO, online convex optimization. So the settings are following. Suppose you have a sequential game that goes from time 1 to time t, and you have a player who chooses xt to play in each iteration from a convex set K, and then the adversary would choose a function for this player to minimize ft from some family of functions. So this function family needs to be convex and Lipschitz. And sometimes you can talk about more specialized setting when this function class is a family of all strongly convex functions. And player incur a loss of ft of xt. Xt is your choice. And then player receives some feedback. Receive some feedback from the interaction, and the feedback is often in terms of the gradient of ft at xt. Okay, so this is the so-called full information setting. Okay, so sometimes you get other settings where you only receive function evaluation. So this is called the bandit setting, because then you have to explore and then try figuring out what this function look like elsewhere rather than just at this local location. And in the lectures that we, in the bandit lectures that we didn't get to talk about in this class, I encourage you to continue reading the OCO textbook. There's a reduction of the bandit setting to the full information setting by somehow creatively choose this xt such that this becomes an unbiased estimator of the gradient. Okay, so there's a third setting that is different to either one of these, is to say that, well, you observe some kind of a noisy approximation of the full gradient in every iteration, and this can be sort of just a generalization of the bandit setting, but the bandit setting is more intricate because you don't really get to approximate the true gradient unbiasedly, but you can approximate a slightly different objective function with a barrier function. But yeah, that's not the point. So the point is that in today's lecture, we're going to be working with the full information setting and also on the noisy gradient setting towards the end. Okay, so that's the setting. And what is the goal of a player? Yeah, there's a question from the group chat saying that is it possible to do online learning for trend filtering? So you are way ahead of the lecture. So that's the last point that I'm going to get to towards the end. So stay tuned. So how are we going to measure the success and failure of an algorithm? So there's this notion of regret that can be written down as t from 1 to t and ft xt minus the best choice xt in the hindsight. Okay, so so this is measuring that after everything is realized, then this player looks back and asks herself, what have I done wrong? So suppose I get to observe f1 to ft at the very beginning. What is the choice that I'll have to? What is the choice that I can take? And how did I do comparing to that fixed single choice? If an algorithm is no regret, it means that it means that for any possible sequences that's can come out in this game, this regret t over t goes to 0 as t goes to infinity. So whenever this happens, we say that this algorithm has no regret, meaning that on average, on every time step where I'm behaving as well as the best expert or the best argument in the hindsight. So another way of talking about the regret, since this x is a minimizer, is that we can also define the regret as a regret against some fixed comparator u, right? So in this case, you basically say I'm comparing against any u, and this regret is parameterized by u itself. Okay, so let me add a little bit of like an amendment to this definition of regret. So let's call it static regret, because we are comparing only with a fixed comparator in the hindsight. We're comparing only with a fixed comparator, while ideally you can compare with a more dynamic regret dynamic sequences of comparator that changes over time. Okay, so it is called static regret in the original paper, in the first work that talk about online convex optimization, Zinkovich 2003. Okay, so let's give an example of why is this static regret setting limiting. Okay, I'll call the example number 1. So let's say that the adversary comes up with a sequence ft equals to x minus t over t squared. Okay, maybe the set is I guess 0 to 1. You can choose any number between 0 and 1. So what is the best expert in hindsight in this situation? So let's add everything up from t from 0 to 1. Ft of xt is equal to sum of x minus t over t squared, t from 1 to t. Okay, so let's try to evaluate what the minimum is. So to do that, we can simply take the gradient, take the derivative and assign it to 0, observing that this is a strongly convex function, we'll get a unique minimizer. Okay, so the gradient is equal to sum 2 times x minus t over t. Okay, assigning this to 0 will give us x is equal to 2t, 1 over 2t, 2 times 1 plus 2 plus 3 plus 2t, right? And that is 2t squared, 2 times 1 over 2 t plus 1. These two got canceled out, these two got canceled out, and then we get what we got what we 2t plus 1. So it's roughly half, right? So choosing half everywhere will be the nearly half everywhere would be the optimal solution in the hindsight. However, if this is objective function that we want to minimize in the first place, even the best expert in the hindsight doesn't seem to perform too well, right? So how do we calculate that? So if we substitute this into this equation, if you substitute the optimal choice into the equation, 2t e plus 1 minus t over t square, yeah, we can write it as t square okay, and well, this is somewhat more complicated when we sum between from 1 to t. So let's do the integral. So let's do the integral so that we can obtain an upper and lower bounds up to a constant. Square dt, and this becomes 1 over 3 t minus t plus 1 to cube, and then this is integration from t to 1, right? So clearly when you set this to be 1, this is negative. When you set this one to be t, this is positive. So we get something that's proportional to t cube, right? We got something that's proportional to t cube, and dividing that by t squared says that the optimal regret is OT. Sorry, the optimal cumulative objective function is order t. And that is really bad because since all we want to minimize is t objective functions, saying that the best you can do is order t, and comparing with this the best static comparator doesn't seem to be the right thing to do for at least this problem. Okay, so if you draw that, so the sequence of f t will look like some linear function from t from 1 to t. It basically grows linearly from 0 to 1. So this is the kind of things that you would expect that the fancy algorithms that we took an entire PhD level course to learn should be able to handle, but it doesn't really. So even though the regret is good, so since this is a strongly convex case, so the regret is proportional to log 1 plus t. But the actual objective function that you're trying to minimize is proportional to order t. Okay, so the best comparator would be here, and then the kind of loss that you suffer is this shaded area, but integrate that with an additional square. Okay, so you can do as well as this, but that seems to be a very low bar to boast about. Okay, so the question is obviously, can we do better? So in the same paper of Zinkovich, 2003, he introduced a concept called dynamic regret. So dynamic regret compete against an arbitrary sequence comparators in the hindsight. So the corresponding regret, dynamic regret, is equal to I guess sum of f t from 1 to t f t x t. So this is the argument that you played as a player minus the minimum of u1 to ut any sequence sum of t from 1 to t ft and ut. Okay, so that's a definition of dynamic regret. So so I argue that in general this is a mission impossible. You cannot actually achieve it. So I'll give another example to illustrate why that is the case. So suppose you have a stochastic adversary that chooses ftx. So at time t before you play, before you receive any feedback, I can choose this ft of x to be x minus 1 square x with probability half, and I'll choose x plus 1 square with the other probability half. Okay, so what is the best expert in the hindsight? Best dynamic okay, so the best dynamic comparator would simply look at all these realized random coins, right? So the best comparator have access to f1 to ft. Therefore, the can simply choose u1 to be either 1 or minus 1, depending on like which function that this f1 turns out to be. Okay, so to be I guess arg mean of ft, ut to be arg mean of ft. Okay, and the mean of ft is always 0. So ultimately, the best dynamic comparator would end up having the sum of ft ut equal to 1. Sorry, equal to 0. Why is it not possible to achieve? Take just one step. Take time t, and then like let's think about the simple problem that the player is facing at the time of making decisions of which x to play. So suppose the player knows that the adversary is doing this kind of random sampling, and then the best that this person can do to minimize to minimize the cost is to come up with x such that it minimizes the expected value of ft. What is that? It's half with probability half. This is x minus 1 square. With probability the other half, this is x plus 1 square. What is the best you can do here? So the best is to choose x to be equal to 0. And ultimately you get 1. And you have to suffer a regret of 1 like in every iteration, comparing to the supposedly 0. Ultimately what you end up getting is that the regret of any player, the dynamic regret of any player is t. Yeah, this is really bad because we can't get any near to the optimal solution that minimizes the dynamic regret. This is saying that in general, dynamic regret is not something that you can minimize without additional assumptions. So what do we do? So yeah, so by the way, like this is not a problem that can be solved by simply restricting the family of functions f1 to ft, right? So you can, even if you restrict it to strongly convex functions, so this is already strongly convex functions. These are all strongly convex functions in one dimension. You can't get any simpler than this. And even in this case, you have a blow up of the regret from log t in the static case to order t in the dynamic case. So what do we do? So there are two family of ideas that are floating around in the literature and in this community on how do we address this problem. So the first idea is that maybe we should just restrict the family of comparators. So instead of comparing to an arbitrary sequences of U1 to UT, maybe we can well, maybe we can come up with some kind of path constraints on U1 to UT, which I'll give an example. So maybe we can consider the family of U1 to UT such that their cumulative changes measured in 2 norm is smaller than PT. So this is what we call a path constraint. Okay, so with this path constraint, then maybe it's possible to come up with an interesting enough regret bound that depends on the path constraint. And suppose the path constraint is sublinear, and hopefully we can get sublinear regret in this case. So this is a setting that was considered in Linkerich and later significantly generalized and made adaptive in Zhang et al. 2018. I think this is an ICML paper. Yeah, the original I think is also an ICML paper. Then the second group of thoughts of how do we restrict the space of the problems so that we can have a more tractable problem family to solve is to, I guess, make assumptions on the sequences of FT that you observe. This is also a reasonable assumption in many cases because, well, we assume that the adversary can choose an arbitrary sequences of functions and maybe even depends on my random coins. Maybe even depends on all the other things that the adversary can be adversarial about. So let's take that privilege away from the adversary so we can compete on a more even ground. I allow you to change this function, but maybe I don't allow you to change this function by too much in every step. Or maybe you can change like the function significantly at one step, but I restrict the number of times that you can change the function that I'm hoping to minimize. Right? So this is a set of very interpretable assumptions to deal with as well. So it's often in the form that F1 to FP change slowly. For example, we can talk about the sum of T from 2 to T, then some kind of a norm between the function itself is smaller than VT. Specifically, yeah, since this is a norm for the function, so think about it as an L infinity norm. Soup of all possible x, absolute value t minus 1, x minus ft x, smaller than VT. And this VT is what they call the variational functional of how this function could be. And this is assumption that's considered pioneered in Bestis. This is operations research. Okay, and later the idea is extended to like a general LPQ norm. So notice that this is one norm. This is like if you consider this function as a vector, so this is a like sum of L infinity norm or sum of arbitrary LP norm. Okay, and you can rewrite this as a like a mixed norm of one infinity norm. So the general case when the path constraint is decided in terms of the general PQ norm, PQ norm when P is larger than 1 and Q is larger than 1. So this becomes something that's more general. It's studied by my co-authors and I. Yeah, also in operations research. So there are like many different variants of these type of assumptions on F1 to Ft. So there's another family of assumptions that deals directly with argmin, right? So consider Xt to be the argmin of Ft. Then you can also come up with a set of assumptions where X1, X2 to Xt. So this minimum solution change slowly. Yeah, for instance, you can talk about T from 1 to T, X T minus 1 minus Xt, P norm, maybe with a factor of Q here. So taking this to be 2, and it's smaller than some variation of constraint PQ, right? So that's an alternative that you can define, like how this approaches would work, and that's just more closely related to the path length type of path constraints, but different because you are actually making assumptions on F1 to Ft. But in the first setting, you are not making any assumptions on F1 to Ft. You're only making assumption about the comparator sequence that you want to compete against. Okay, so this setting, so I think one of the first work there is Yang et al. 2016. It might be in Europe. Yeah, so besides these different assumptions that get it to work, so you can also think about all kinds of variations to the problem. You can talk about the general convex function. You can talk about strongly convex function. You can talk about different feedback structures that your algorithm may see, right? So that includes like the full information feedback, like which is assumed in this case. You can talk about the noisy gradient feedback, which are the setting of this and that. You can talk about the both. You can talk about the banded feedback as well. So that appeared in this paper. There's a lot of variations that we can talk about here. So let's focus on like 2 simple examples. So these are the settings that I consider the most interesting and most general. So we'll talk about the full information setting. In the case when we are dealing with path constraints. So that's the first thing that we're going to be talking about in the remainder of the lecture. And the second thing that we're going to be talking about in the remainder of the lecture is the noisy gradient feedback, but in this form, under this assumption. And the first, it's going to be under this assumption, and then the, I guess, full information feedback. There's related intricate ways, but I'll leave it to you guys to explore if this is a topic that interests you. And the noisy gradient feedback. In the same sense as a stochastic optimization, when you have a noisy stochastic gradient that's observed, so it's under the same model as that. And the full information feedback would be something else where you observe the full gradient. But notice that this is not a full gradient of the whole thing, right? So this is a full gradient of every individual data point that you receive. So these 2 settings are might be more closely related than you think, and the full information might not be more restrictive than the noisy gradient feedback in a more stochastic setting. Okay, so so again, let's write the regret. The regret. So the regret is now parameterized by 2 things. is parameterized by t, we parameterize by u1 to ut. So this is a fixed, any fixed comparator that you want to talk about. So, so this is equal to, again, ft xt minus ft ut. And you want to bound this using some function of t and then the path constraints of u1 ut. Okay. In this case, the pt is equal to the sum of ut minus 1 to norm and sum over t. Okay, so it turns out that like online gradient descent itself is a working algorithm in this setting, and we'll get some non-trivial regret bounds of even if we are talking about a sequence of comparators in the hindsight. So this is the very general algorithm that we talk about in OCO. So that's the first algorithm we talk about that applies to general convex function, which updates a parameter using projection to the convex set k xt minus eta t gradient under the full information setting. So at time t+1, you basically play xt plus 1, right? Using only the information from the past. So we've shown that this algorithm has a static regret of g times d times square root of t. Okay, so just a quick recap. So what is g? What is d? So g is the upper bound of the gradient at any location. Okay, so we assume that these functions f1 to ft they are g Lipschitz. Besides the assumption that they are convex. What is d? D is the diameter of the space. So this is an upper bound of any u1 and u2. So this is smaller than if u1 and u2 is inside the physical region K. Right. So basically on the boundedness condition, then you can get a static regret from the online gradient descent and have a static regret against any single comparator u. So what Zinkovich proved, so this is theorem 2 in section 2.2 of (2003). So it says that if you choose this learning rate to be a constant, then the dynamic regret with respect to any sequences satisfy a path constraint PT, it's smaller than okay, and then you can choose this eta appropriately. If you choose this eta optimally, you can show that this is this is on the order of square root of t d square plus LD times G square. And yeah, L is PT. Okay, so notice that the path length goes into the picture. So and the dependence on the path length is square root of the path length. Okay, and suppose the path length is equal to 0, then this reduces to the static regret case when you become simply GD square root of t. So we'll see how this works. Okay. So the proof relies on exactly the same techniques that we've learned before in working out the static regret bound for online gradient descent, right? So it becomes like very, very transparent. So we rely on like two conclusions. I'll derive them. Don't worry. But these are things that we've talked about when we work out the regret bound for online gradient descent. So by convexity of ft, and for any u in this class K, like we can use the definition of convexity and get the first order condition. I'm using GT to denote the gradient of ft at xt, u minus xt, right? And if you just move things around and then you end up getting per step regret bound, just move this just move this to the right hand side and then move all the other things to the left, and then you get gt xt minus u, right? So this is the first thing that we're going to be using by simply applying the definition of convexity. And by the OGD algorithm, we can get xt plus 1 minus u is equal to, let's apply the algorithm. So this is a projection to this convex set K, xt minus eta gt minus u. Okay, so this is simply by the algorithm. And then, as usual, we'll expand this and then try to construct the xt minus u square out of this. But first of all, let's deal with this projection. Since projection is a non-expansion and the u is assumed to be inside the convex set, u is inside the convex set, and then we can just bound this by simply dropping this projection. All right, and well, this is equal to xt minus u by simply expanding this, by simply expanding the quadratic term, eta t gt square minus 2 eta okay. So this is the second thing that we need to use. And the third thing that we need to use is, well, let's maybe further expand this, yeah, actually, like, why don't we stop here and then we'll come back at the 212 to talk about how to continue this analysis on the dynamic regret. All right, yeah, take a break and then we'll be back in 212. All right, it's 2:12. Let's resume the lecture and continue our proof in the dynamic regret bound of online gradient descent. So the one thing that I wanted to point out about these two expressions is that well, the first one uses convexity so that we can bound the suboptimality using the linearized term, so that we can get a regret bound. In the second one, we can further upper bound this gradient, this linear term using everything else. By moving everything else to the other side, then we get a further upper bound that controls the regret. So the thing that I want to point out is that in this case, this U can be anything. So it doesn't have to be the static regret bound. So let's maybe take this U to be UT. Okay, so if we take U to be UT, and then we get xt plus 1 minus UT smaller than xt minus UT plus 8 gt squared plus 2 eta gt x minus xt minus UT. Okay, and then let's apply this one to be UT as well. And then we end up getting the thing that we can upper bound. But well, there's one trickiness in later. You must have already seen this. In that previously we're constructing the telescoping sums, right? So when constructing the telescoping sums, we need this these two terms to somehow cancel out. So ideally, in order to construct the same kind of telescoping sum, the trouble is that here this is UT, but not UT plus 1. Okay, so that's the next fact that I want to just write down. So fact 3. So this is well, we can decompose. We can decompose this by just subtracting and adding UT plus 1 back. And then we can just expand this term and get xt plus 1 minus ut plus 1, get the thing that we want, plus ut plus 1 minus ut. This is something that you can imagine that you get a bound that's that comes out of the path length constraints, plus x minus ut plus 1, ut plus 1 minus ut. Right? Like the three simple facts. And with these three simple facts, we're already ready to prove the regret bound. So in every iteration, we can bound ft, ut by using the fact 1, right? We'll bound it with gt, xt minus ut. And using step 2, using fact 2, we can further bound this with 2 eta xt minus ut plus gt square minus xt plus 1 minus ut square. Right? So this is applying the second fact. And now let's apply the third fact by replacing the last term with the complicated things right here. So we'll get 2 eta xt minus ut square minus xt plus 1 minus ut plus 1 square. So this is coming from here. Minus ut plus 1 minus ut minus 2 times xt plus 1 minus ut plus 1 ut plus 1 minus ut. Right, and there's one last thing that we didn't write, is gt squared. Okay, now let's apply our assumption on the Lipschitzness of the functions, and then also apply Holder's inequality to this. So we can write 2 eta. So everything that we want, so let's keep them. So let's drop all the troublesome parts. So this is smaller than 0. So we can bound that with 0, and this is smaller than eta square g square, and this is I guess by Holder's inequality, it's smaller than the by Cauchy-Schwarz 2, and then ut plus 1 minus ut 2, and with an additional factor of 2 here. So what we will end up having is something that's slightly simplified. Plus 1 minus ut plus 1 square plus 2. Well, further we can bound this with the diameter that comes from the definition of diameter. So 2 diameter times ut plus 1 minus ut norm plus eta square and g square. Okay, so now everything seems to be a very nice telescoping structure. So let's sum up. 1 to t, and we get the t minus ft ut. And this is smaller than 1 over 2 eta. And everything got canceled out except for the first one. And the, I guess, and the last one, t plus 1 minus ut plus 1. So ut plus 1 is not really defined, but it doesn't matter because this term is negative. We're going to drop it anyways. And plus 2d and sum of ut plus 1 minus ut, sum from 2 to t, plus t times eta square and g square. And then let's bring this 1 over 2 to eta inside, and then drop this term that's negative. And we and then substitute the definition of the path length. And we end up getting d squared over 2 eta plus g squared t. So this comes from the last one, and then plus 2d times the path length over 2 eta. Okay, so this completes a proof of the theorem. By choosing, if we know the path length ahead of time, then by choose eta to be d squared plus dpt over square root of tg. Okay, and then you can show that this is proportional to actually thanks to the 1 over 2 factor, we don't need to write the big O. T g squared d squared plus d times 2t. And that's it. Right. So if you look at analysis, it's just a very like minor modification of what we already have when analyzing the gradient descent. Okay, so I'm gonna make a few remarks. So first of all, this bond is optimal. This is information theoretically optimal in T and PT parameter, but the algorithm, OGD algorithm, cannot compete against all U1 to UT simultaneously. Yeah, this is in some sense necessary, like in a sense that like we're not actually restricting the sequences of function to be to be somehow stable at all. So suppose you choose this U1 to UT to be something that changes very rapidly, then intuitively OGD shouldn't be able to do it well. And specifically, OGD is not able to achieve that kind of optimal bound unless you know which sequence you're competing against. Okay, so it doesn't really adapt to the sequences of comparators. And for each sequence of comparator with the same pass width, you have to know what the pass width ahead of time before designing algorithms that's optimal for that family of comparators. And suppose that like you may argue that you can maybe choose a pretty lenient upper bound of PT, but then you are losing out. You are not getting the same benefit that suppose the actual sequence that comes out. Suppose a comparator, the sequence of that come out requires you to use a sequence of comparators that doesn't change nearly as much. Okay, so ideally we want to design so-called adaptive algorithm. So adaptive algorithm, when PT is not an input. Okay, in this case, you can argue that you can simultaneously compete against all sequences of U1 to UT and then getting the optimal bound. Okay, so this is a problem that AGD cannot solve, but a solution is given in Zhang et al. 2018. Adaptive algorithm in PT, and I think they use some kind of exponential weighted averages, like which we talk about in this class. So that's on this hash algorithm. So you can think about that what they did is a clever implementation of the hash function that manages a bunch of OGD with different learning rate choices. Okay, it's called adder. So another thing to note is that if PT is chosen to be 1, you get the static regret bound. Suppose you choose PT to be T, so this is what happens in example 2. Then you get the trivial regret, the trivial dynamic regret of T. Okay, so in some sense, this is a slightly more general treatment than what you would get suppose you make assumptions on the functions. Like especially since that now that you have an adaptive algorithm. Okay, so so the next thing I'm talk about is to give you another example on this other side of the story. Suppose we make assumptions on function variations. And then we're going to be assuming noisy gradient feedback. So again, as a reminder, the function variation is defined as follows. Where Vt is a constant that depends on t, and it can grow with t, and this like it's just measuring like how quickly that these functions can move. And since we are allowing the noisy gradient feedback, which essentially says that like each one of these f instead of one individual data point can be the changes in the population quantity. And suppose you are getting one stochastic sample from that population that allow you to construct a noisy gradient. And this assumption is not about how individual data points can change, but rather than how the underlying distribution of these data points can change. So this assumption could potentially make sense. Suppose these distributions are only driven by, say, a sparse number of changes in the history and so on. Okay, so this is a natural setting. And again, the feedback model is you get GT is equal to the gradient at your location that you choose plus additional noise, and this VT is IID sub-Gaussian noise. Yeah, actually, it doesn't have to be identically distributed. So independent sub-Gaussian noise. Okay, and the regret that they define is a in some sense expected regret, since this is in this stochastic gradient setting. The regret is t from 1 to t, ft and xt, and this expectation is taken over the randomness that you receive this noisy gradient minus where xt star is equal to arc mean of ft x. Okay, so notice that any regret bound that you would obtain here would also give you a regret bound that covers all possible comparator sequences, but in a much weaker sense. In a sense that the kind of regret bound that you end up get is going to be a function of t and this path variation vt. And this path variation vt, like you can use it to construct upper bound of x1 star minus x2 star plus xt t minus 1 to xt star, right? So in some sense, like this is closely related to the maximum of all u1 to ut that's meaningful of this pt. So you don't have to go above the variation of the pointwise optimal solution, because beyond that it becomes not meaningful anymore. So in some sense, the reason why like this can compete against all sequences is because you're taking the maximum anyhow, and the bound doesn't work. It doesn't give you like the best thing that you can end up getting. Suppose this ut to u1 to ut is chosen to be something that changes a lot slower than the pointwise optimal solution. Okay, and the algorithm is also related to OGD, but let's state it in a slightly more general form. Okay, so the algorithm will take any will invoke a subroutine called A. So this is any OCO algorithm with static regret bound. Okay, and then the algorithm is like I'm gonna split the entire sequence of t into batches of delta t. This is the batch size. So think about this is entire sequence 1 to t. So let's decompose it into, let's partition it into fixed sequences of individual like subsequences of size delta t, right? So at the end of the day, you have t over delta t, ceiling number of sequences, and the algorithm, like for instance, you can take this A to be just online gradient descent, and then this becomes so-called restarting online gradient descent with a fixed restarting schedule. OGD with the restarting schedule. So basically, you run OGD from here. You restart. You run OGD here. You restart, and then you only run OGD within every bin. Okay, so that's the algorithm. So how does it work? So this is proposition 2 in that space, and this should be part of your reading list before the lecture. So we can show that the regret bound of t as a function of t and vt, this is smaller than the number of times that you restart multiply with the regret bound of this subroutine algorithm A on that particular sequence plus 2 times the batch size times the total path variation. Okay, so think about this as a general like reduction lemma that allows you to reduce dynamic regret minimization to static regret minimization, since you're just cleverly invoking the same algorithm for every batch. Okay, and the proof of this is actually pretty straightforward. Let's start with the definition of the dynamic regret. Right, so you are comparing to the pointwise optimal solution, xt star. And well, let's further decompose it into the different batches from j to 1 to t over delta t. So I'm going to skip the ceiling. So let's for now assume that t is an integer multiple of the chosen batch sizes. Tj from 1. So this is individual index within each batch. And then I guess you get ftj, xtj. Let's subtract the xtj, xj star. I'll define what is xj star shortly. Minus ftj xtj star. Okay, so I define this xj star to be the arg mean of sum of ftj ej from 1 to delta t. So this is the like the sequences of functions that you receive within the j's within the j's beam, and then this is a fixed comparator in the hindsight for that beam. Okay, so once we do this, we can group the first two together and group the second two together. And notice that the first two, once we group the first two together and add everything up, so this becomes something that we can make use of the regret bound of the subroutine that we called within every chunk. So this is smaller than t over delta t. So this is the number of times that we need to invoke it, and each time it has a regret of that's given by its regret bound. Okay, and well, how about the second term? So so in the second term, we're going to be trying to bound it using the path variation and delta t at the same time. Star. Right. Like it takes a few steps, but let's see. Let's call this star. This is star. So the idea is that I wanted to somehow show that like within each batch, if the function changes only a little bit, then the pointwise optimal solution like isn't really that much better comparing to the fixed comparator in the hindsight. Okay, so I guess like how we're going to be doing that so let's define a function called 1 over delta t and sum of f tj from tj from 1 to delta t. Okay, so this is average. This is average function in the hindsight of this sequence that we receive within a beam. Okay, so this star can be rewritten as a sum over j. This average function evaluated at xj xj star. Okay, and then I think I need to multiply delta t, which is cancel things out, right? So this is a function, right? This is function. I'm just rewriting this in a slightly different way. ftj 1 to delta t and ftj x star tj. So this is a pointwise optimal solution as usual. Okay, so the first thing that I'm going to apply is to apply the optimality of this xj for this for the sum. So xj is obviously optimal for the sum. Therefore, I can replace xj star with anything else. So I'm gonna replace it with average of with average of xtj star. Okay, so I can always do that using the fact that xj star is optimal. It's optimal fixed comparator. I'm replacing that with a different fixed comparator, and this one is obviously going to be worse. Okay. And now let's make use of the definition of convexity. So to notice that each individual ft is convex. Therefore, like the sum of it, any linear combinations, non-negative combinations of these functions are also going to be convex, right? So we can apply we can apply the definition of convexity, or equivalently the Jensen's inequality, right? By saying that this function evaluation at this point is smaller than the average of the function evaluation at every single location separately. Right, so we can further bound this with 1 over delta t is sum of t j from 1 to delta t 1 over delta t tj from 1 to delta t ft. So again, this is a whole function that we're looking at, xtj star. Okay, and then I minus with ftj of xtj star. Okay, now these two can be grouped together. So notice that this is this function let's call it f2.j is a linear combination of individual terms. It's actually a convex combination of every individual ft. Therefore, like using the path variation, I can show that for any ij that's in the I guess j's chunk, j's being. Using the path variation, so we can decompose the path variation into the sum of vt j. Okay, so within the j spin, so if you pick any I1 and I2, then this fi1 minus fi2 in L infinity norm needs to be smaller than vtj. Therefore, we can bound this term, we can bound every difference within this summation by, let's move to a new page. We can bound everything of that summation by delta t times j delta t times v tj. Yeah, so this is the most tricky argument that I'm gonna have today. So wait, where is it? Yeah. Yeah. So basically, the average of this function, like I'm basically just using triangular inequality. So I'm arguing that since the total number of moves within this beam so the cumulative move within this beam is smaller than vtj. Therefore, if you pick any individual points and then take the difference of that, it's going to be bounded by the cumulative move. So I'm bounding individual moves from any like time t to time t, at most t plus delta using this vtj. And notice that the partitions are predetermined, so it only depends on the j's on the j speed. And this obviously becomes VT smaller than VT and delta T and VT. Okay, so if we collect everything together, then we get that the dynamic regret bound is smaller than T over delta T times the regret of A for a sequence of delta T plus delta T and VT. And if we use OGD on convex function, under this setting, so it's stochastic, and it doesn't really change anything because we've seen that in subgradient descent, whether you have stochasticity doesn't really make a difference. So the regret bound is T delta T square root of delta T and dg, and g squared plus sigma squared. So this is something that you should have worked out in the paper, sorry, in the homework. And in the second step, you have this VT, and this is if you choose this learning rate appropriately. If you choose this delta T appropriately to balance out these two terms, you will get the T to the power of 2/3, and then the VT to the power of 1/3. If you use OGD for strongly convex function, what you get is T over delta T, and then log 1 plus T, right? Log 1 plus T, maybe divide by the strong convexity parameter, and times G squared, plus this, and again, if you choose this delta T appropriately, you will get square root of T, square root of log T, G over M, and yeah, I think I missed VT in the square root G. So this is proportional to square root of T, VT. Yeah, square root of T VT. So in other words, so whenever VT is sublinear, whenever the variation is much smaller than the length of the sequence, then you can end up getting an interesting and non-trivial no-regret algorithm that compete against much stronger sequences of comparators. Okay. Now, maybe let's go back to this example 1, right? So in example 1, we said that this ftx is equal to x minus t over t squared. So this is really, if we generalize this a little bit by saying x minus theta t squared, okay? And then suppose you observe the gradient in every iteration. So what is the gradient? So the gradient is 2xt minus theta t, okay, plus noise. So suppose this is what you observe. And notice that you actually know what xt is, right? Since this is the argument that you play. So essentially you are getting a noisy approximation of theta t. You get theta t hat, which can be written as this gt divided by 2, and then minus, and I guess plus xt, right? So this will be theta t plus a noise, that's zero mean. Right. So essentially in this case, the kind of feedback model that we get from Besbis et al. Is like in this special case is it's just a noisy like noisy observation. So this setting in statistics is called non-parametric regression. So you get to like at least in the hindsight. So based on the observations that are the noisy version of the ground truth, and how do you somehow smooth the signal and denoise the observations so that you can hope to estimate hope to come up with theta, I guess an algorithm that takes all the theta 1, yeah, let's call this yt to avoid the confusion, minus theta t square and sum of the t. So this is a mean square error, right? So suppose you so this is a non-parametric regression problem when you assume theta t changes slowly, right? So there are a lot of like standard literature from the non-parametric regression that makes assumption about how theta t can change. And in the simplest case at the beginning, like we're talking about the linear changing of this theta t. And in this kind of a path length assumption, then if we assume that the theta t minus 1 sum, and if we assume this is smaller than say pt, and this is saying that this theta vector is in the total variation ball of pt. If you in addition assume that this theta t minus 1 square root is smaller than pt, this is saying that the theta vector is in the Sobolev ball of parameter pt. If more generally, if you do sum of t, theta t minus 1, p norm 1 over p, right? So there are other functions that you can talk about, and in particular when p goes to infinity, and then this theta is in the this is the family of Lipschitz functions that's called the Holder class. A Holder class that parameterized by this parameter pt. Okay, so in all these families, you actually get know the minimax rate. You actually know, like in the offline algorithm, how you are able to end up estimate this ground truth theta with noisy observation. And the online algorithm that tries to achieve that is, well, the online algorithm that tries to achieve this goal is to put additional restriction to your algorithm so that you can apply this algorithm online, right? Therefore, the lower bounds of these problems should directly apply to the online problem at the same time. Like, however, if we look at say, take the simple example and then the most general one, so this is a total variation bounded sequences. So we know already that in these sequences, in the offline problem, the optimal rates, the optimal rates is t to the power of 1/3 and pt to the power of 2/3. Optimal offline rates. It turns out that none of these algorithms that we talk about so far can actually achieve this rate. So this is strongly convex. Therefore, from best bits, you get something like this. You get this rate, and you need to somehow convert this VT into PT. But this is the rate that you got. And using the standard online gradient descent with a fixed comparators, you also get yeah. Alternatively, you can actually think about this problem if you receive the gradient of this, the gradient of this would give you would be equivalent to the to observe YT. So the amount of information is the same as plus noise, right? So in this case, it's equivalent to the noisy gradient kind of setting, and using the Zinkerich style argument, and using adder, and using the methods that's proposed later that tries to be adaptive here. All you can get is actually also t squared pt. Okay, so like this is actually not surprising at all because these like square root of t rate is a lower bound for a family of methods called linear smoothers. So suppose you are sticking yourself to computationally efficient methods called linear methods, that takes any linear transformation of your input observation, then this is the best rates that you can hope to achieve. And you cannot actually get the optimal rates of t to the power of 1/3. Actually, having a t to the power of 1/3 rate in the adaptive online learning type of literature is unheard of, like for any kind of problem. And this one, like although it's highly specialized, it talks about like a strongly convex case, not just strongly convex. It talks about a quadratic case in 1D, but it's quite remarkable that in this special case, you can hope to maybe achieve t to the power of 1/3. And this is a problem that my student and I tackled last year. So this is Baby and Wang, 2019. And then you can construct an algorithm that achieves this rate in the dynamic regret minimization setting. Okay, so I'm towards the end of the lecture. I just want to mention that all the references that I talked about and these two examples that I gave are not the only ways of making online learning algorithms more adaptive to changes and to non-stationarity. There's also a family of so-called strongly adaptive like regret minimization problem pioneered by Daniel Lee et al. Like this is not the first paper there, but it is one of the most general. There are other extensions of that later. But let me tell you what the notion of the regret here is. So strongly adaptive regret with a length tau it's to say that for any subsequences that's in the form of q plus q, from q to q plus tau inside the region from 1 to t. Okay, so for any subsequences that you got, and then you can talk about regret. You can get a regret bound as a function of tau. So this means that like if there are changes and you can simultaneously compete against all these localized oracles that does optimally in that local region. So this is yet another way of trying to make online learning algorithms more online, which I unfortunately won't have time to talk about it, but it's definitely worth another lecture. Yeah, with just 5 minutes left, I wanted to I wanted to say a few things about the general content of the lecture, and then say some final words as you go ahead and then bring these techniques to real life and to applications. So these methods comes from convex optimization, is significantly developed in the machine learning literature, and there are interesting connections to game theory, to problems in statistics, in information theory. So I hope this experience of working out some of these regret bounds and convergence analysis can be helpful and helps you to and these practices help you to become more mathematically mature, to tackle problems in principled ways rather than just coming up with some solutions and then evaluate everything using the experiments that you choose, right? Because like in terms of research, some of these methods are not yet practical, but give it a few more years, and that maybe this algorithm will become more practical, and maybe as people gather more information more efficiently, and then you really have to be like more adaptive and more adversarial in your point of view about the world. And the second thing that I want to talk about is where you apply this technique to, where you apply the optimization and machine learning, and then in general artificial intelligence techniques, because where you apply these techniques actually matters. So you can think about optimizing a classifier to help local businesses to survive, to control the pandemic. You can also talk about building a company that build a classifier to to classify whether a person is a terrorist or not based on just the facial expression, right? So there are good things that you can do. There are also bad things that you can do. So the techniques themselves are not guilty of the deeds that people decide to use them for. And it is you who wield this big hammer, who needs to decide to put this to good use cases and to be sensitive to the fairness and privacy and all the other social issues that are out there, right? So being sensitive to all these problems are also part of the important training to be a more sensible human beings and let alone getting a PhD from UCSB. All right, so that echoes my background today, which is actually Santa Barbara. So this is the recent demonstration in front of the courthouse in Santa Barbara, where people stand together to share their to I guess to share their feelings towards towards George Floyd, who were recently brutally killed in this incident. And then I think this is really an issue for all minorities to stand together and to fight against racial discrimination and other things. That's really important. And if at someday in the future I can see some of the AI techniques that's being used in these applications that helps the world to become a better place, I will be extremely happy about everything that I've spent to teach people about these topics. All right, so that's all I wanted to say. And thank you all very much for being a great audience. And yeah, unless you have questions and comments and any final thoughts about the course, I'm gonna say goodbye. All right, yeah. Thank you all. And enjoy the summer.